talk called Addiction and Speed. Usually I do really boring talks about the innards of VMs. But I'm just going to talk a little bit of personal history, which is about addiction and speed. And then I'm going to show you some code, which I think is speedy. So for those of you who don't know me, I started off in '83 with a summer job and then a student project, and then my virtual machine was used as a research project when I went to Queen Mary Westfield in the University of London, and then from there I became the VM engineer at Parklands, went to California, and became tech lead. Come on. And did the first 64-bit Smalltalk, and then at Quack, which became Teleplace, and eventually Attend, I started the JIT extension of the Back to the Future Squeak VM, and then at Cadence, I did the.
Just speak louder.
At Cadence, I did Spur, which is both 32 bits and 64 bits. And then over the past sort of the 5 years from 2018 to 22, trying to make what was Quack work, take the 64 bits and try and build a market, and failed. And recently I've been rescued, and with the Priest team helping, Priest at Labware helping Labware go to 64 bits. So this is Queen Mary Westfield. This is Richard Bornat. About that time, he had darker hair, and he's the head of department, and he was a COP theorem prover guy, and he loved ML. But really interesting guy in the department. Sorry, it's not him. That's me. Is this?
Come on.
No. Maybe he's trying to hit on me. I don't know. Peter was bisexual. He had a tooth that was cracked from the middle of his teeth to the corner. He smoked Gorvars, chain smoked Gorvars. He refused to use a computer. He had all of his office full of information on the Kennedy assassination. He invented the virtual machine in the year that I was born. He defined the SCCD machine. That's Peter Landin. And we used to meet in the bar. Meet in the bar. Can you hear me if I speak like this?
Yes.
No. So,
the recording.
Wonderful. Oh, well, now I'll have to record like this.
Speak as loud to the.
So, Peter used to ask me how Smalltalk worked, and he would regurgitate it in the lambda calculus. And so I learned the lambda calculus because he was one of the inventors, with Strachey and all of that guy. So Peter was an exceptionally colourful and interesting man. It just made me think about computing, forced me to think about computing in a more general way. I loved him, he was fabulous. This is Richard now, and Richard wanted us to have cool machines, and yet he thought that you should do computing as a rewrite exercise. He was a mathematician, right? Computation was rewriting. And so I would tease him that all of the undergraduates should put their assignments under his door and he should complete them with pen and then return them. But asking Richard has a different meaning. So he decided that we would all have these AUX Apple machines that ran this Apple Unix, these Macintosh 2s. And it came with a card game, which is better than FreeCell. It's called Sea Haven Towers, and it's crack cocaine for computing people. And the whole department got addicted to it. So the way it works is you're only allowed to move a card to the same suit, and you can move the 7 of hearts to the 8 of hearts. Right? It has to be to the next one. So you build sequences, and let me explain the game this way. So here we go. This is a modern implementation. And of course, being such a young thing, I need my glasses, except I think
Where we are after.
usually they're on my head. Well, I'll figure it out. We'll hold it there. But so you can move anything up to a space, right? And aces, and then the subsequent cards go onto the bases on either side. But the only thing that can move into an empty space is a king, right? And so here we're blocked, can't make any more moves, right? So you have infinite undo, and so that the thing is fun, right? It's all about sequence and solving, and it's a little bit more difficult than free cell. But the issue is this genius scoring scheme, which is that if you don't touch a card, you can have another deal without losing a point. But if you touch a card and you don't solve it, you lose a point. So you have to look at it and figure out, can you solve it? And it's hard. And we loved it. And Richard said, I think I can build a solver in ML. I think the right thing to do is like move something down. If you can move a card down, you should move it down. Don't you think? And we all thought we didn't know. Then he went away and he wrote the solver. But to use his solver, you had to type in the damn data. So Bill, who was a master's student who decided he didn't want to do a PhD and instead became the manager of our IT effort and ran our email service, he sat there on the Mac, this implementation, and wrote a program that dumped the paste buffer to text. And he would move a card and dump the paste buffer, and move a card and dump the paste buffer, until he decoded how the game was represented in the paste buffer. And he packaged it up and he called it Ask Richard. And you would run Richard's program in 2 clicks, you'd wait about 10 minutes, and it would tell you. And then you'd go on and pay. The whole department spent hours and hours and hours and hours a day doing this. So, let's fast forward. I'm going to do this one. Fast forward to a delightful and painful period in my life from 2018 to 2022. So this is Verten, as it's called, but it's was quite. It's the extension of Alan Kay's and Andreas Raab's and David Smith's Croquet project, right? And it's a shared 3D space with you can scrape desktop applications, webcam, and so then we have Outlook. Not Outlook, whatever the presentation thing is in Mac. And it was great, and I had to do all sorts of things like learn how JPEG images and MPEG images and video streams were changed and add echo cancellation. But we failed, and it was depressing. And by August of last year, I don't know if you've ever been to Lahaina in Maui, but Hawaii is a very, very beautiful place with very, very calm and generous people, and I love it. And it was destroyed. And if you look at this picture, you may ask yourself some questions, and that's all I'll say about it. So I was in November so depressed that I found this game on the web, and I started playing it, and I found that it was a piece of shit. It was like, occasionally you would tap a card twice and it would move one card down, and there was a ghost card, and then undo didn't work. And sometimes the solver here, you see that there's a hint there, and if you ask that, it will tell you what to move. So that's actually a searcher looking for a solution that will tell you what to do. that would take more than a day, or more than overnight. I mean, many hours. And I thought, you know, Richard could do it. I bet I could do it. And so I started, and I made the same mistake as Richard. I typed in the data. So I would sit there, and you know, the first extension was an error checker. The data, I never typed it right. There were always 3 queens of spades or something. It was agony. But then the many delightful hours of profiling and trying to figure it out goes. So let's go back to this game and think about the strategy. The obvious thing that we need to do is we need to do a search, right? And a depth first search is not going to work, right? Because you're going to go off down some rabbit hole, and it's going to take forever. So if you're going to do a breadth first search, the challenge is there are moves which will get you into a cycle. Like you can move any card up to a space, and you can immediately move it back. So you have to avoid going where you've gone before. And so the obvious thing to do was to try and record the state of the game so that I could keep it in a canonical representation and know that I'd seen another state before. So if you think about it, if kings could go up to the columns, then if you make 2 columns free, you could put a king in either column, right? So you need to sort the columns and maintain the columns sorted on the top card. And if you do that, right, it doesn't matter how you get to any state, every state is represented in exactly the same way, right? Because the first card is sorted. Right? So that was the first thing to do, was to figure out how to represent the state and how to keep it sorted. And then I could produce a hash function and just use a dictionary of previous states and keep the thing working. So if I inspect this guy, the first thing to
Could you
think
make
of
the
was...
font bigger? Could you make the font bigger?
Yes, I can. Let me do that. I can't remember what it's called, but it's a factor. No, that's the wrong scale factor. Because I set it to 2.5. I know it's already 2.5, so that's not the right one.
Front side?
Windows, visuals, or something like that. Yeah. All right. I don't believe this, but anyway, we'll try 2.5 and see what happens. Oh, you were right. I'm sorry.
That's good.
I
That's good.
apologize. This is great. So let's take it down to like. Oh no, it's because I scaled it to 2.5 when it hadn't connected to the overhead projector. Now I understand what's going on. Okay, so let's try 1.5. All right. There we go. Is that okay? Do you think?
No, that's
Still small.
4.75. Hang on. Let's get that. Scale factor. 1.75. Oh, the Greek interface looks so great. Okay, there you go. Is that all right?
Yeah,
Yeah.
it's better, yeah.
Okay. So I think I have my inspector. Here we go. So the first thing was to figure out, okay, how to represent it even before I could take a hash function. And I realized that the byte is the ideal thing, right? So a single byte, if I use 0 as null, and I arrange that each suit is a subset of 16 values, then each suit ace is going to start on 1, 17, 33, etc. And the king is going to be 13 further. So there's like This kind of thing, right? Subtract 1, set modulo 16, and if it's 12, etc. Then so divided by 16 gives you a soup index. So now I can use byte arrays, and the virtual machine copies byte arrays very quickly, so I can copy a game state quickly, right? So where am I in this? So what we're doing is we're trying to produce a hash so that we can compare these things. It turns out that this thing went through some interesting evolution. And so you can imagine that the right way to do it is you have an initial state and you have a dictionary of states and you have a legal move generator that generates all of the moves from where we are and adds them to the pool, and then goes through the pool with all of the new states and does the legal moves for them, and any that are already in the pool get truncated. It turns out that when you push all of that through and you found a solution, how do you print the damn thing? What you need is you need a predecessor link. Each state needs to know the state it came from, so that when you find the solution, you can actually print out the solution, which is what you want to do. You want to win the damn game, right? So I, worked on solving it, and then I couldn't print the data, so that was silly. So when you do that, and you have a predecessor link, then you don't need the hash at all. All you need to do is arrange that you are not going back to a state that you've already come from. And if you go to the same state somewhere else in your search, and you get to exactly the same point, it doesn't matter because you're doing this breadth first search. And in the breadth first search, you will always get to the nearest solution first. Right? So you'll never waste any time looking at this thing twice, because if it's on the right way open, these things go parallel. And it turns out that then, instead of maintaining this huge dictionary which balloons to thousands of states and you're spending all of your time looking at it, you save some of your time just looking back at your predecessors, that you can throw that away and not use the hash. So that was kind of interesting. And so let me show you what the legal move generator looks like. So, oh no, let's not do that yet. Right. First of all, we have to see, can we beat this thing? So, okay. Back to my slides. This is a comparison of this third generation iPhone SE against this first generation Apple Silicon M1. And there's a bit of difference, right? The M1 is a little bit faster, but this thing is essentially unity. It's essentially the same speed, it's like 86% to 90% depending on the benchmark. So we can actually think of these two things as the same, which is astounding. I thought that this would be like 5 times slower or something, but no, it's not true. So what I want somebody to do in the audience is look at their watch, and what I'm going to do is I'm going to say restart, and when I say restart, it is going to go dark, it's going to go grey, and it will go white when it's figured out the next move. When it's done a complete search and it knows the next move, okay? So you have to time it for me. So that that's what we're talking about. So restart. And now it's gone, so you're timing it, right? I have not been able to play this since like last week. In other words, I had to keep this one so I can demo it for the talk. Like the first thing I'm going to do when I finish is like play another game or something. Finish this. So how long did that take?
A little over 16 seconds.
16 seconds. I'll take 16 seconds. So okay. So there am I, like a buffoon, like Richard, typing in the data, and I'm finding bugs, and I think, okay, let's go into help. And it's got report game. I thought, let's complain to the developers and say, look, I've got a better solver than you. But look, there's the game state. But that one's no good, because if there's a column which only has 4 cards in, right, then that last row is all shuffled along, and it's no longer in the line. There's no click. So I wrote an importer from that, and then realized that that was done, that wasn't going to work. And further down is, of course, the lovely XML. So, select XML. And the ghost of Steve Jobs comes to your rescue. And say, copy. And then, go in here. And say, so what I've got here is from clipboard, which imports the XML, and then breadth-first solution. So this captures the solution, and then what we're doing is forming an array with the time to run, and then we ask that to print the moves. So we're going to get both in the solution. So there it is. Copy the data, and it takes 3.5 seconds. So I don't know what this is made of. Objective-C, C++, whatever. But whatever it is, it's so bad that they can't write the correct solver. And if you do the Smalltalk right, you can beat them hands down. So.
Yeah.
So now we can have a look at kind of what the thing does now, and I won't belabor the point, but I'll give you a small. So the API is find a breadth-first solution, which depends on all legal moves breadth-first do, or breadth-first solutions, in which case you collect them, or you can decide that you're going to look to a particular depth. So this is the one that we're using, and all legal moves breadth-first do is let me drag this onto the straight away. It's the most incomprehensible Smalltalk you've ever seen, because to save time evaluating doing an instance creation of a block in a loop for each set, I allocate the block once at the start. So I'm doing strength reduction by hand, right? To say, because when you copy one of these states, you've got an array of the 10 columns. So you're copying the array and each of the 10 columns, and then the object itself, and then the 2 arrays for the spaces and the bases. So a closure in there is noticeable. It's going to be like 5% of your allocation, right? So you want to avoid that. So you can't make sense of this algorithm anymore because you have to like mentally put things in. So what it's doing is it's grabbing the current state from all of the states that we've generated from the last algorithm, right? So we start off with one state and we create some number of states of all of the legal moves, and then we move forward from there. Right? So we're moving forward this frontier of states, and we want to ask each state, are you stuck? So there's a thing that happens, because you've only got 4 spaces. As soon as you get 6 cards in a line on top in a column, and there's one of the same suit lower than it, it's stuck. Because you can't move these 6 cards. You need 4 spaces to get rid of 4 of them, and then move one somewhere else. Right? So you can move n plus 1 cards. So you can figure out if a state is not worth pursuing, and that's important. Dropping the search tree. And then we want to find out if it's new, because it's only worth following if it's new. And so new used to be, if novel used to be this really complicated, let's hash and look in a dictionary of states and having all of that memory. But now it's much simpler. It's just, let's go and have a look at our predecessor and ask it, has it seen it before? So it's just, and these things are like 35, 20, 40 moves deep, right? So they're very, very quick. So that's very simple. And so if it's not stuck and it's novel and it's solved, then you evaluate the block, but you add it to the set of states, the next states that you're going to explore. And so the loop is just through the current states, apply the outer evaluator, and the inner evaluator, and then replace the current states with the next states that you've got. And the only other thing to give you is like one example of a legal move. So, for example, this is the method that is where's the sample? So here's the legal move generator with some piece of debugging in it that I don't need. And so you just enumerate over all of the possible moves from the spaces and all of the possible moves from stacks to stacks, stacks to spaces, and then consider moving any top card of a stack up to the space. And so those are the three, and they all look more or less like this. They're very straightforward. So this one goes through the spaces, and if the card that you find in the space is a king, that can only go down into an empty space. So you search for a nil in the array of stacks. Otherwise, you compute the card that it's going to go onto, which is one higher than it, and you search through the stacks for a stack that ends with that value. And if it does, then you create a copy of yourself where you have moved that card to that space, right? And evaluate the block with it. And that's it. So it was really nice to find that you could express it clearly enough that you could obviously get it correct. Because the guys who did it in the iPhone app did not manage to get it correct. Right? Probably because they had something that was taking 8 hours to solve difficult things rather than a few minutes. Anyway, that's it.